will be different, and this will be different. And let's go to the next one. Sorry guys, due to time being, I need to explain the rest of the things also, so that's why I just skip this some of the part. And here is a minimum reinforcement. How much is the minimum reinforcement we need to provide? So if it is a side reinforcement, when we will go for the side reinforcement, if suppose this is a beam, okay, so beam will exceed a 750 mm depth. So if it is a 8 mm depth, 800 mm depth, then you need to provide a side reinforcement. Exactly, here we will get a reinforcement. Here we will get a reinforcement. We need to provide a side reinforcement exactly here. Okay, so that is we how much provided? 0.1% of the web area. How much area will be here? So just provide a 0.1%. Okay, spacing is not exceeds the 300 mm. Suppose this spacing will be not exceed the 300 mm. If you wanted to provide, you can provide a 2 like that. Okay, so and here is a minimum percentage of reinforcement. Compression members shall not exceed 0.4D, and here is the minimum reinforcement, shear reinforcement, all the information you will get here. Okay, every time whenever you are going to read our code books, try to highlight important points. So every lot of information will be available here, but at least we need some information related to our work. So if you are dealing with the construction buildings, so you don't need to focus on bridges and these are transportation. Just study whatever the points in a construction related. So you need to focus on those only. Minimum, maximum slab diameter. How much is the thickness of diameter? 1/8 of the total thickness of the slab, diameter and slab. And here is a in case of maximum shear reinforcement in beams. How much is the maximum shear reinforcement? ASV by BSV by 0.87 FY. Okay, the shall not be spacing exceeds 300 mm. Okay, so here we have it's an important concept actually, but I feel it's very sad to neglect this one. And the deep beam, if you are going for the deep beam, when you will divide the deep beam, so when we will decide is it deep beam, L by D is 0.2 for the simply supported beams, and is 2.5 continuous beam. L we know, depth we know. So then if you ratio of that LVDV, it is a 2.0, then we call it as a deep beam. Okay, and here again go here, the sizes and partition of the ribs, and again here is some of the ribs we have some flat slabs, waffle slabs and like that. And if you go for the flat slab, so the flat slabs is the main thing is if you go for the flat slabs is always designed with the one-way shear and two-way shear. We call it as a punching shear. If it is a punching shear, where we need to, if it's a punching shear, how can you take it? In the footings you can observe here. So this is a punching shear, and here we will get a column. So D by 2 distance, the punching shear will be acted D by 2 distance. Okay, so where we will take the D by 2. So if suppose this is a slab with the drops and columns with the column head, you need to take from out of this column head to here, it will be the D by 2. And here if you don't have anything, so D by 2 will be so exactly column from column to D by 2. And if you have some this one, and here drop with the column with the column head, so column head here we need to take a D by 2. So punching shear as a main governing factor in a flat slab design. Okay, and come to here, next. Yeah, so here the minimum reinforcement ratio of vertical reinforcement of gross area of the concrete. How much is the gross area of the concrete for the walls? If you design a walls, how much is the minimum reinforcement we need to provide? 0.0515. Okay, for the type of bars, and is the deformed bars. If you go for the deformed bars, 0.0012%. Okay, so 12.2% like that. And here is a distribution stair, and this is a footings. How much is the span and the next meters, and how it will be divided in the ongoing, and like this. And here is also slab distribution. It's a cantilever, how the loading will be acting on this, and like that. And it is a footings where the footing will be the footing stresses will be transferred from this column to exactly in this distance. Okay, so this is a gamma. There you can get a gamma from here also. Here is a C, tan gamma is equal to 0.10 ck, and you get all the this QU is equal to calculated at ck. These all things you will get here. And again go to here, and the last one, yeah, limit state, and all these calculations will be here. And you can set a cracking, how much is the cracking, it will be affected, and partial safety factor. This is a important thing is a limit state of collapse and the limit state of serviceability. So when we will go for the limit state of collapse and the limit state of serviceability, whenever you go for the footing design, we need to go for the limit state of serviceability. why we will do that? So every time whenever we do the SBC calculation, there the geotechnical engineer will take 2 to 3 for the partial safety factor. So if you are again, if you are taking the P load, so axial load, if you take a 1.5, so it will be giving you the higher reinforcement and a higher size of footing. So at the time, already they taken SBC value, so partial safety factor. Why can't you take a P load? So that's why we will take a without a partial safety factor, we will take only P. Okay, so here if you see 1.5, 1.2 and 1.2, 0.9. 0.9 will be acting as a overturning forces. And come to here, so here you can see, while considering the earthquake effect, the substitute the earthquake load for wind load. So yeah, what IS code suggests you, so whenever you are designing a building, so these two loads will never act at any time. What are the two loads? Earthquake and wind load. You didn't face that. So tsunami is also came at once the earthquake will come. Okay, that situation will be not occur. Okay, just we are assuming. But if you take these two loads acting on at one instant, at the time what will happen? Your reinforcement will be going to higher. So if the reinforcement will be higher, unnecessarily you are increasing the project cost. So the client will may gone. Okay, so that's main thing. And here is the limit state of collapse. If you go for the collapse and flexural compression and also some shear, and these are the formulas. These all we know that. Okay, design torsion and these are and deflection cracking. So and if you go to the annexes, so here you can get all the working stress method and again some of the calculations we can see here, deflection calculations, and even if you go here, and this is yeah, come on. Permissible stresses, working stress method. And again, let me show you that. So some column, how we can decide the column, we know that. And here is a calculation of the crack width. If you want to calculate the crack width, how we can calculate moment resisting for the rectangular and T beams. Okay, these all things we know that. And so let me show you some of the IS 800 peak. So before that, let me try to cover some construction peaks actually. So for you to understand better understanding. So see this. And again, so here you can see the pipes. Okay, these are the pipes we are using, and so for the 𝗏𝗏 pipes when we are doing the concreting, and then this is some of the what is the quick setting and micro cement concrete. When we will use the micro cement, that will I tell you. So this is a type of testing we will do. So once we done the concrete, see this. So slump cone, we will cast these cubes. So these cubes, and this is a concrete equipment, and here is a flow of this, and so you can see, and we will check the sump clone. So and so after that, this is a type of happen in a site actually. So whenever the improper vibrating, then we will get some type of issues here. So at that time, what we need to do, we need to go for the micro concreting. So if you go for the micro concreting, we need to touch up. Okay, we call it as a touch up in a site. So we need to use the micro concrete. We will fill this all the gaps. Okay. So micro concrete gives you the strength, that is some JK you seen, right? So this is a micro concreting. Okay, so based upon that mix, and we will do this is a slump test. See this, how much slump it is acting, and we can see. And this is see guys, I hope you understand it. And this is a bucket. Okay, this is a bucket for doing the concrete in the columns or anything. And here we have some crane. Okay, so that crane will give you this bucket, and once you lift here, so somewhere here we have a lifting. Then if here you can see, here you have a lifting. If you just remove, move this, and this entire portion will be trained by upward. So at the time, and it will be happen. See this, and after that, this is a mixed design concrete. It's I hope see this 20 minutes. So this is how we can check the level of that slab. So slab level is correct or not? How we can check this thing. And here is a concrete mix plant actually. So here you can see here, this is aggregates. Once you send it to this aggregate to in this and some of the pipes will be here, and here we have some that office. In that office we have all the missions and type of computers there. By using the computers, then you can if you wanted to show the here you have some silo types, right? In these silos you will place the concrete and these things. Once you give an input in a computer, then that how much is a concrete, how much is a cement it need to release, that will be released here. So like that you will get a concrete. And this is a compression stress mission. And after, see this how we can use the gunny bags to cure. So this is how we can curing it. Okay, so by providing the gunny bags, and here is a, this is a starter. Okay, I hope you can see here, this is a starter. So yeah, see this by using the total station, we will mark exactly in this position. We will make a starter, exactly we will place a shuttering here. Out of this we will place a shuttering. These are the marking for the shuttering. Okay, exactly we will place shuttering in this, and here we will place a shuttering. So like that we can use the shuttering. And again come to the next one. Yeah, this is see guys, this is how we can arrange it. Before that, even though see initially it is it's showing you some sagging, right? Yeah, see this. So evenly, see here we are getting some deflection. Okay, so after you are adding the concrete, how much deflection you will get? So those things we need to study. Okay, even initially, see this, initially it gives you some type of bending. Okay, so once concrete will done, it may going to, concrete is a heavy weight. So this is the column junction actually. So you can see here as how the junction will be look like. And even just imagine the 20 mm aggregate will be passing through easily or not. So, and I hope I need to understand. And these are the admixtures. 𝗵𝗲 is an admixture, and one of the admixture we are using. And these are admixtures. Based upon these admixture, we will increase into. And here is some 𝗚AC type of brick. So 𝗚AC type of brick will get 100 into 200 into 600, and it's giving you a less weight. And this why we will make this arrangement. See this, what will happen exactly at this condition. In the below of this column, we are getting some seepage, water seepage. At the time, what we did, we just make some sand here, and after that we will water some water exactly here, and after that we just place a cement. Okay, so what will happen through that water, the cement will go and fill that gaps. So that is what our concern. Okay, so main these type of things will happen in a site actually. So see this, this is a seepage will happen in at that site. So I hope you understand. So to rectify this, we will use that water with cement. Then that cement. This is whenever you have some type of see the double platform. So try to make a platform in the ground level. Okay. So don't go for the double staging. So that will lead to a lot of problems. Okay. Try to make a platform here. So here you will never get a, see in this level. This is a ramp actually. So the ramp exactly in this height, it will get a some two height. So it is a 3 meters, and here is also 3 meters. Throughout the 3 meters, we never ever get any slab. At that exactly here, I need to provide a slab. At the time, how I can provide it? We need to make a staging. So otherwise, don't go for the single props with staging. It will never help you. So it will lead to some problems in a site also. So after that, we can't do anything. And this is how we will make a reinforcement for the staircases. Again come to here, and this is how you can see, and this is how we can arrange the slab depth exactly. Here you can see the line door. So based upon these wooden this, and we will check the leveling. Okay, exact leveling, how much is the leveling there. And here is a sump cone again, and here is sump, and these are the cubes. So these cubes also, I didn't find that where we will get that cubes in IS code book. So I already seen that based upon the how much is the concrete will arrive reached into the site. So that much cubes we need to cast it. Okay. So here we will cast it at 3 samples. A sample in the sense of 6. In each sample we will get a 3. And this is a ceiling. How we can provide a ceiling by using the aluminum. So most of the beams will be covered in this in this ceiling also. Okay. At the time you don't need to worry if suppose anywhere in the slab in the hall you will get any beam. So if it is a ceiling will be available. So the most of the ceiling will be in that slab only. So the no need to see this type of what will happen here. So workability will be increased. So this will happen. So due to unnecessarily so actually what happened at that time. So yesterday, the day before the day, so exactly this day, so yesterday was happening, a rain happened, so that's why, so we are getting some this water cement ratio will be increased, so that's why this is happen at the time. Okay, so these are the hilti boards. So whenever if you want to do, suppose you are doing anything wrong in the construction, you need to provide a hilti. So hilti, I hope you know that. So this is how we can do the arrangement. This is a hilti. So here you can see it, and based upon the in this here in this pipe you will get a hilti. So this is a 𝗵𝗕 mission. There you can see that some chemical is in this inside. So that this is a cantilever. So you can see here, if it is any cantilever is there, how we can provide a cantilever. So here we will get a maximum depth. Why? Because the moment will be higher in this junction. So wherever we have a fixed in this cantilever, there we will get a maximum moment. So to resist that moment, we will increase the depth. So this is a purely, so here is the total station points, and after that you can imagine it. Can you the 20 mm aggregate will be go inside of this. So at that time you need to go for the some 10 mm aggregate also. Okay, so most of the mixed designs will be included with the 10 and 20 mm. Okay, so these are the steel structures, these are the columns. So the whenever if you go for the PEB structures, you can find out this, and PEB with the columns, these are the columns, and here we have holes, and this is we call it as a haunch connection. Okay, and so yeah, these are the purlins, cleats for the purlin. Okay, so side, and these things, yeah, let me show you that. So see this, this is a cleat. So whenever you get a purlin, so you will get a purlin here. Purlin also we have a C type and Z type and C type. Okay, whenever you get a purlin, here we have a holes like this, and in the purlin also you will get a holes, and there you can place it, and this is for the bracing. Okay, X bracing. Okay, these holes and these will be for X bracing, and here you will get a stiffeners, and this plate will be for the rafter connection. Okay, when how it will look like if you go for the steel structures, if it is a PEB, so you will get like this. Okay, so here you will get a base plate. Okay, and exactly here you will get a again the rafter. Okay, this is a connection, and this is a plate, splice plate. Again you will get a rafter here, and again it will be look like this. Okay, this is a again it will like this, and here you need to, if it is a PEB, you will get a this type of arrangement. Okay, so it's a PEB, some other concept we will cover in the steel IS code books webinar. Okay, so and again come to here, this is a welding mission. So welding, okay, whenever if you are built up sections, so ISMC, ISMB, these all will be somewhat another sections. So welding sections will be somewhat built up sections. We need to weld it. So here you can see exactly, here you can see the welding. So yeah, see this one is a weld, and this will weld here. Okay, so exactly top also we will weld it. How we can weld it? So not by through mission we will weld it. So this is the mission for welding. So it will go around like this, and here somewhere here we will do the welding. Okay, manual. This is a footing center line, and based upon this, how we can like the column, and here we will get a column here exactly. Okay, so after that you need to provide a reinforcement like this. Okay, so you will get a reinforcement like this exactly, and the column will be like this, and this is a center line for the footing and the column. Okay, so I hope you know that, and let's do the next one. And again, this is a mixed design actually. So see guys, let me show you that. So after the mixed design, the concrete, every time if you go for the concrete vehicle, there you will see it. Okay, the product code, and how much is the sand we will use, and how much is the R sand 1 and 2, 20 mm aggregate, and 10 mm aggregate, and fly ash, how much content of fly ash we use, and CMT, cement, and water, how much is the admixture we will use, and based upon this you will get a error percentage. Okay, how much we need to added as per the mixed design, how much we added. So based upon that we will get a error percentage. So these are the error percentages. Okay, I hope you understand it. So let me go for the another IS code book, IS 800. So IS 800 is mainly for the steel structures. Okay, if you go to here and see guys, I already covered this IS steel IS code books in last webinar. So I hope I don't want to do some time actually in this. And materials, if you want to study the material, go for here. And design requirements, mainly tension reinforcement, sorry, so what is that? See, this is a limit state of design, and design of tension members, compression members, and it, come to the tension members, we have some due to yield cross section, and these all things. Okay, so and here is a compression members. Compression member is a slenderness ratio and buckling characteristics, and it is a plastic member, compaction member, and this is subject to the combined forces. And here is a working stress, and here is a design detailing, and so how we can detail, and durability, fire resistance, fabrication, and erection. So this is erection is also main important thing, and whatever the designer will give, that will be mainly, if it is a correct, no need to worry about erection. If suppose the designer will designer or detailer will give the some wrong inputs, so wrong drawings, then erection team will be may suffer. So erection team needs to face a lot of issues due to this improper detailing and drawings. Okay, so we need to very cautious about that design. And in steel structure, in RCC we can maintain it, but in the steel, once it will be fabricated, we can't do anything. Okay, we need to collapse that entire plates, and we need to again refix it. That will leads to higher cost. Okay, and come to the IS 16700 SP16. Okay, what's SP16 is mainly for the design aids. Even let me show you what are the design aids we need to follow. So some of the design aids, come here. Here you can see the content actually. So in this we will only discuss the content, the grade of the concrete, type of the concrete, and reinforcement, how much, and the flexural member. If it is a flexural member, how can you design the under reinforcement section, double reinforcement C section, control of the deflection, and the compression member. If it is a loaded compression member, axial loaded, uniaxial, and the compression, slender shear and torsion, these all things. Okay, and here is a somewhat singly reinforcement. How if it is a 𝗵𝗂 15 and FY 250, how much is the depth, and these all things you will get from the page 17. So like that. And here is a control of the deflection formulas, and axial compression, and some of the compression with the bending, and these all things will be here. So let me show you those also. Some of the curves here, and you will get a see here exactly. You can see here some of the assumptions, and so here we will see the formulas actually, formulas, and step by step under reinforcement structure and balanced structure, over reinforced. If it is a singly reinforced structure, singly reinforced beam, so we can see all the procedure here. Okay, so one thing I suggest you to just take the any of this IS SP16 and take this singly reinforced beam. You can go to the Excel sheet, and you can as it is, you can type in Excel sheet making with the formulas. Then after that, anytime if you wanted to do the singly reinforcement, by just giving Excel sheet input and output, then you will get a exact sum. Okay, whatever you need. Okay, all our designs will be mostly done by the Excel sheets. Okay, try to learn the Excel sheet design, and so once you know how we can do the formulas in Excel sheet, that will be very easy every time. You don't need to go for the manual calculation every time. So if you have Excel sheet, then you can do it the Excel sheet by giving some inputs only. Okay, every formula will be same. Okay, so and here is a doubly reinforced beam, determine the main point. So this is a doubly reinforcement, and even though our see, let me show you that one how the ETABS will calculate these settings. So if you let me show you, so ETABS also follow all these code books. If you go to program files, and here is a structures and computers, and 2016, and some verification, analysis, design examples. If you wanted to see some design frames, so here you can see that. And if you wanted to see some technical notes actually, so get manuals, go to the manuals, and here is a verification, some design, and here is a concrete slab. Here you will get all the code books. See guys, if you wanted to do the PT, so post tensioning, here is an example how the ETABS will calculate based upon the IS 456-2000. So ETABS already done the manual calculation for this. So based upon that manual calculation, all the design will be related to that. Okay, this is not by any IS 456. This is generated by CSI, computers and structures. So here it will take the post tensioning slab, and as per the IS 456 PT slab example 1. So based upon that, they verified that. So verified results, see here also. So future tested and independent results done by the manual calculation. ETABS will do the calculation. How much is the difference? 0.0% is given by the difference. So mild steel reinforcement 1.25. So they already tested manually. So they will conclude this one. So this much of difference will showing you the ETABS. Okay, so if you wanted to see the calculation, you can see here. So every calculation as per the 𝗚𝗚 x by d, xu by d. Yeah, this is a this is a formula for xu by d, right? So and also if you go to here, this is a so let's see another formula. Here is mu is equal to mu by bd square by fck, compression block depth. Okay, xu by d, and ast is a mu by 0 fy by gamma s, and like that. Okay, so this is a post tension, right? So 𝗖𝗓s also follow the some of the manual calculations. Okay, based upon if you wanted to see the RCC, so you can see here. So this is a structure they took, and here as per that, and they do the this one, and 𝗖𝗓s calculated, and here is a calculated. How much is the difference we got? 1.757. Okay, this is how they can calculate it as per the 𝗚𝗚 whatever the formulas we use in our manual collection, they only use that calculations. I hope you understand it, how we can do that. Okay, so and after that again just go to here. Yeah, let me show you. And the design aids also main important. These are design aids only followed in the 𝗚𝗚s also follow these design aids. Okay, so based upon these examples they do that. Okay, so these are the some charts. Okay, so yeah, just go to the downside. Some of the development lengths also here. So here you can see all this. So some of these are the charts and these things. And if you go to here, so let me show you some of the development length they mention. So after the calculation, they will show you the development length. How much is the development length? LD, yeah, here is you can see it. So development length. This is a formula which we discussed earlier. And see this, and as per this development length, no need to calculate manually. They will give you tension bar, grade of the concrete. If it is the diameter, it will be the 10 dia. How much is the, if it is a M15, how much is the development length you need to take? And if it is M20, how much is the development length? If it is a compression bar, how much is the development length you need to take? So in the tension, it will be increased, and compression it will be decreased. Okay, compression is mainly strong in a concrete. Okay, so that's why it will be decreased. And again, here also same. Okay, like that you can see here also it will show you how much is a hook we need to provide. So here you can see the 4 into 4 into dia minimum. Okay, so and here is a k into dia. How we can calculate the k? So here we can see the k value, minimum value of k. So like that you will get it, right? So these are the uses how we can use the SP60. And come to the next one, IS 875 part 1. So I hope so let me conclude this by discussing these things. And part 1 is mainly for the dead loads. Okay, it's a dead load in the sense, so if you come to here, some of the aspheric material and blocks, bitumen and black dust and 𝗕𝗕 and cast iron, all these material dead loads will be here. Okay, if you see here, yeah, this just go here. Let me show you only here only. So in this we can't we didn't study somewhat little in this dead load. So here is, if you suppose it is a broken aggregate, so how much is the aggregate? If it is a sand will be dry or clean, river sand, wet sand, how much is unit weight you need to take? Kilonewton per. Here you can see the values, meter square or meter cube, and this will be getting. And how much is 18,000 kg kilonewton. Okay, so if you wanted to get the kgs, here you can see 1843 meter cube. Okay, kg per meter cube. So like that you can get it. Okay, all these will be same. And even if you go to the last also same, all the materials, whatever the materials we can use it, those all materials will be here. Okay, so based upon that we will took the some mortar screeding or ISMC. These also will get all the mass, how much mass it will be, and like that. Okay, and let me show you that. So I hope you understand it. And come to the live load. Live load here we need to discuss a little more actually. So come to the live load. First we need to study the table 1. Okay, so in this here we can see the terminology: imposed load on due to occupancy, imposed load and live load reduction factor, position of the floor capacity, dust load and impact allowance, and crane load combinations. These all you can study here. Okay, so and if you go to here, and this is the main important thing: imposed load for floors on a different occupancy. If it is a residential building, how much is the kilonewton per meter square load I need to take? All rooms and kitchens I need to take a 2 kilonewton per meter square. How we can take, where I need to apply? Okay, just go to 𝗖𝗓s and just see here. This is my slab, right? So just imagine this is my kitchen. Okay, just imagine this part is my kitchen. Okay, whatever the slab I selected, this part is my kitchen. How much load I need to apply as per the S code? It will say kitchen I need to apply the 2 kilonewtons. Let's see how much I applied in this. It is a roof actually, so that's why I applied 1.2. Yeah, where is it? Yeah, see this loads. Just go to loads. Here 1.5 kilonewton per meter square is the live load. SDL in the sense superimposed dead load. I applied 1 kilonewton per meter square. Why I applied 1.5 in the roof floor? Why where I get that 1.5? So that I will explain you. Here toilet, if it is a toilet, 2 kilonewtons, and corridor, and it's a 3 kilonewtons. Balcony, 3 kilonewtons, right? And dwelling units and hotels. If you suppose you will go hotels, that people will be somewhat large. Okay, at the time you need to go for the higher. If it is a kitchen, so this is a 3 kilonewton. But here residential building 2. Okay, from here only we need to take it. Okay, so this is all the different type of educational buildings. So somewhat the storeroom. If it is a showroom, all the books and everything will be placed. So there is a maximum load here. Okay, so at that time, and here is imposed load: dining rooms and cafeteria and assembly buildings and business and office buildings. And these also banking halls, mercantile buildings. Mercantile buildings, all the I mean, we can place a lot of stuff in that mercantile retail shops. So we need to take, and industrial building, and these all things. But here also you can see number of floors, the roofs carried in this. If you go for the live load reduction, so how we can reduce that? If it is a 1-story building, we don't need to reduce it. If it is a 2, we need to 10% we need to reduce it. And here is a 20% for 3 and 30% for 4-floor buildings. If it is a 5 to 10, we need to reduce the 40% of live load only. So if it is over 10 floors, G plus 10, we need to reduce a 50%. 50% of live load we can reduce it. So that as per the IS code book. Okay, and now come to here. Yeah, imposed loads on roof. Okay, so imposed load on roof. Let me tell you. So I took a 1.5. Why I took a 1.5 in my ETAPS model? So imposed loads on various type of roofs. Access provided, access not provided. What is the access provided? Access not provided. If suppose you are providing any staircases, it will call it as a access provided. Access provided to the roof. So I provide a roof staircases here. So that's why I took a 1.5 exactly in my ETAPS model. And access not provided. If it is an access not provided, if I didn't have any staircases, I felt it's a access not provided. Why? Because if you are providing the staircases, all our parents and everyone go there, and in the roof floor they will walk around it, and the load will be increased. So that's why we take it as some different load also. And here is a single roof floor with a slope greater than 10 degrees. So this is whenever if you go for the PEB building. So how much is the live load we need to take? PEB in the sense pre-engineering building. So live load we need to take a 0.75 kilonewton per meter square. So we need to take a 0.75. But come to the US codes, they suggest you 0.57 kilonewton per meter square. Why US codes giving you some lesser load as compared to Indian codes? Due to some machinery, and these all things will leads to heavy loads in our India. Okay, India is not having this technology like that. Okay, and the skill labor also not that much skilled. So that's why we need to increase ourselves. So that's why they increase those. And again come to here, and these are some of the horizontal loads on a parapet wall and blasted. Okay, so and if you go to here, and how much is the percentage of here, and you can see. And this is the main thing. And if you wanted to study more about the loads, and even you can see here also how much load will be reduced. See here, yeah, the floor, it's a number of floor. It's the first floor. Okay, this is a first floor, and how much we need to reduce? This is the actual load will be 30 kilonewtons, but we take as a 30 kilonewtons. 0% I need to reduce as per the code book. In early we seen, so 0 for a 1-story building. Okay, so if it is a 2nd-story building, how much I need to reduce? 10%, right? So for that I need to take a 1 by 0.1, 10%. And if it is a 3rd floor, how much I need to reduce? 20%. And the 4th floor I need to 30, and 5th to 10 floors 40. Above the 10 I need to take a 50. So that's why you can see how it will be reduce the load. It's a 40, 50. So 40 minus is a 0.3, and here is a 0.4, and here is a up to 10 floors. Up to 10 floors, all these 10 floors, it is a 0.4 only. And after the 10 floor, it is a 0.5. Okay, here you can see the 0.5. Okay, 0.5, 0.5. Like that, you can reduce the load as per the imposed load as per the IS code book. Okay, and the next come to the wind load. The IS 875 Part 3 2015 wind load, and come to the wind load. So wind load is also main important thing. So yeah, this is a zone map showing map of India. Basic wind speed. How much is a basic wind speed we are getting in every city? So here you can see all the information. See this, and we have some 55 and 50, 47, 44, 30, 36, and 39, 33. Okay, so this is the basic wind speed. Come to Vizag. How can you know Vizag? If you are suppose you are doing some G+10 story building in Vizag, how can you know how much is a basic wind speed we are getting? We have some formulas. So what are the formulas? Vz is equal to K1, K2, K3, K4, K4 into Vb. Vb is the base shear. Okay, so let me show you those formulas also. Here, this is a general information. No need to worry. And here you can see design wind speed, Vz. So whatever we see as per the map, that is a basic wind speed, but we are designing the wind speed based upon the basic wind speed. Okay, so see here, Vz is equal to Vb, K1, K2, K3, K4. What is this K1, K2, K3, K4? If you got come to here, so K1 is a here also you can see. So K1 is a probability factor, risk coefficient. K2 is the terrain factor, topography factor, importance factor. So how we can decide it? How we can decide these things? From the table, K1 risk coefficient. So based upon the life of the structure, if suppose you are designing for the building with 100 years, at the time you need to go for the with this one, and my K will be as per the IS code book, my wind speed will be 50. If it is a Vizag, it's a 50. So how much K I need to take? K1 1.08. Okay, so it's a final. And after that, so next will be so K2 terrain category, table 2. So K2 will be height multiplier. If suppose my building will be G+10 story building, so it's nearly 30 meters of height, right? 30 meters. Here I need to go for 30. And how much terrain category? 1, 2, 3, 4, 5. So how we can say that my building is in a category 1 and category 2? And I think I think we didn't have any pictures in a terrain category here. Just imagine what is the terrain category in the sense how many buildings surrounded by your building with some of high-rise buildings. Okay, if you suppose, let's say, if you have a building is a 30 meters height. Suppose you have a 50 meters building with nearly in our 100 meters from your newly proposed building, we have a 50 meters height. Here also you have a 40 meters height. At the time, what will happen? So these buildings will take this wind load. So you will never get that much wind load in this exactly in this edge. So that's why if it is having some high-rise buildings, we need to go for the category 4 and category 3 and category 2. Okay, based upon that, we will design a category. And again, category 3 factor, topography factor. Topography factor is a K3 is a, so here you see here the slope, windward slope will be more than about 3 degrees. If you have a slope like this, here you have a building, and your ground will be like this. Okay, so you have a slope will be 3 degrees. So slope, this is your building. Okay, slope will be 3 degrees. At the time, you need to go for the 1. If it is a more than, the range will be more than 3 degrees. So more than 3 degrees, we need to take a 1 to 1.36. Okay, and importance factor for the cyclonic region. If suppose you are building in a cyclonic region, right now my building is Vizag. At the time, what we need to do, if it is an industrial structure or all other structures, how we can decide it? All other structures we need to go for the 1.1. So if it is an industrial structure, I need to go for the 1. It is a structures with a post-cyclonic importance for the emergency service, such as a cyclonic shelter, hospitals, and schools. At the time, we need to take as a 1.3. Okay, based upon that, you can decide. If it is an offshore structure, the factor shall be based upon the, in addition to K4. This is a K4. You need to increase the 1.15 factor. 1.15 factor, we need to increase it. Why? Because if it is offshore, the wind velocity will be somewhat higher. Okay, so that's and design wind pressure. So here also we have a formula. Design wind pressure, Pz is equal to 0.6 Vz square, and Vz is comes from the top, and Kd, 𝗂𝗃, 𝗂𝗃, these are all the formulas. And if suppose here we have two formulas, F is equal to CF into A into PD. So this is a one formula which is used for the RCC structures. And if suppose you are going for the steel structure, you need to use this formula. CPI is a coefficient factors. So CPI is external coefficient, CPI is a internal coefficient. Internal coefficients depend upon the area of the openings you placed, and A is the C here. A is the surface area. If suppose a surface area G plus 10 story building, your surface area will be this width direction. So you need to take it. PD will be calculated from the above formulas. Okay, PD is the design wind pressure. So, and here is some of the openings. Openings will be 5% wall area, and we need to take a 0. Plus 0.2 minus 0.2, and here is a building with the minimum openings and 5 to 10%, and plus 5 and minus 5, and openings is larger than that one, 0.7. Then we need to take a 20% of openings. We need to take a GPI. Okay, CPI is this one. And if you have a canopy with roof, canopy, what in the sense, guys, don't worry, I am taking some time actually, so don't worry about it. So if it is about beyond our session limit, don't worry, please. If you want to stay with us, no need, you can stay. Otherwise, if you want to leave with this timings, you can leave it. But I don't want to miss this concept, so that's why I am worried about it. Okay, the canopy in the sense, if you have a column here, so you will place a splicing here. So here we can place a canopy like this. Okay, in this this will be act as a canopy. Here we will provide a jet purlins exactly here. Okay, you will provide a sheeting. So sheeting will be like this. So wherever we are opening here, exactly some opening for the vehicle, you need to go inside, and here we will have a rolling shutter. So rolling shutter. At the time, you need to provide a canopy. If it is a canopy, how much is the length and width we need to take? Those things you can see here. Okay, and this is how the intervals we need to take, and the coefficients also. And again, if you go to here, and this is a main important thing actually. So walls on rectangular cladding buildings. Every time if you go for the RCC building, we need to take this formula, these code books, and H by W. H is the height and W is the width, and L by W. L is the length and width. And here you can see, if you take the elevation, so W is a width and H is a height. So based upon that, you will decide which coefficient you are in, CPE, and for the surface. So if it is a G power 2, and B in the sense, if it is a plan view, so this is a B, and this is a D, and this is a C. Let me show you in ETABS. Just give me a minute. So how we can apply in a ETABS model? So just go to define and click on load patterns. Once you go to the load patterns, here we have a wind load in X direction. Modify the lateral load. All the whatever the input data we studied in that code book, we need to give here. Exposure to the diaphragm extent. If you go for the exposures or shell objects, we need to make some non-walls. We need to assign these coefficients only. So we need to assign the coefficients exactly here. Okay. So if you go for the diaphragms, it will be. And here see wind speed. How much is the wind speed? Terrain category. Which terrain category I need to give? Importance factor. So 1. And the risk coefficient, topography, and this exposure height. Every time wind is only acting on the ground level, not a footing level. So that's why we choose a ground level. How much is the parapet wall I need to give it? So this is how we can give an input as per this IS codes. Okay. If you wanted to go for the manual calculation, you need to go for this content of table. Okay. So based upon this, we can calculate the CPE in that formula. F is equal to CPE minus CPI. Then you can substitute this value in this CPE. Then you will get a F. F will be kilonewton per kilonewton. Okay. So force. So then that will be, you will get, and to here, this will be pitched roofs. Every time if you go for the PEB, so suppose pitched roofs are PEB. So these are the PEB look like this one, right? So at the time you need, so whatever the CPE values we took, that will be mainly for these columns. And these columns and gable columns. So here we have a gable columns at the end of the PEB. Okay, end base we will get a gable columns. Here you are applying the load here exactly like this. Okay, in the 90 degrees and 0 degrees. Okay, 0 degrees. Sorry, it's a 0 and it's a 90. Okay, so like that you can apply it. And see, whenever if you wanted to consider the load on these roofs also, we need to take this table 6. So exposure on a pitch roofs and rectangular clad buildings. Okay, so here you can see the wind angle. How much is a 90 and a 0 angle, how much, and here we will get all the values. And this is if you wanted to calculate the local coefficients, you need to go here, and this is the plan view like that. And if you go exactly here, and this is wherever you are taking the combined effect, the wind load of the frames will be the reserved factor will be KC. KC is a KD, 𝗂𝗃, 𝗂𝗃, right? Those KC will be taken from this, and also another formula will be here. Let's give a minute. Yeah, these are the some monotype mono roofs actually, monotype. And every time if you go for the some foreign type, so there you will get all the buildings will be like this. Okay, so some of the buildings it's a sheeting here and like that, and you will see those type of buildings at the time. So we can do how we can do that building also. These are the arches. So arches how we can design, and so let's see. So we have a lot of concept here. Okay, whatever the concept is mainly for you to do design, and you need to learn here. Okay, this is a main formula we can use for the RCC. Okay, so CF is mainly for the see here we have some tables for the CF. Yeah, this one. So CF is mainly for the CF H by B. From here in this table, in this graph, you will get a H by B. So here is a by B and CF. So A by B in the sense A, B. So A by B, how much you will get, and how much you will H by B. Here is this will be A by H by B. Okay, HB is the sense this one. So based on the H by B, you will get a somewhere here the CF. CF is a some 0.1.2. Then you need to multiply in this F is equal to CF. There you need to place a 0.1.2. Then you will get a so force. How much force is acting? That is a force we need, right? So wind load in the sense force. How much is a force is acting on that? So here is some of the lot of information will be here. How we can design some what is that? Whenever if you go for the highway, so there you can see the some of the hoardings also. Those hoardings also based upon these. So here also you can see those hoarding designs also. Okay. So I hope yeah. See this one important thing: basic wind speed. How we can get the basic wind speed? If you see here, let me zoom out a bit. Yeah, based upon the cities, if it is a Bangalore, how much is the basic wind speed? 33. It's not that much high. Okay, if you go for the Hyderabad, it's a 44, and Vijayawada it's a 50, and Visakhapatnam is a 50. We are in some high zones, right? I mean, we are in the sea zone. Okay, so that's why it's showing 50. Okay, and like that we have, and these are the basic wind speed. Based upon this basic wind speed, we can calculate the design wind speed. Once you calculate the design wind speed, we need to calculate. How let me show you one of the manual calculation. Then you can able to understand easily. So give me a minute. Just somewhere we have a manual calculation. Let's there I mentioned as a formula, exact formula how we can do that. So let's I think I don't know where I put. I need to show you actually. One minute, guys. Manual calculation. Yeah, earthquake manual calculation. Wind load manual calculation. Where is wind load manual calculation? Yeah, see this. And some earthquake manual calculation also I need to show you. So based up, if you know the manual calculation, you can understand how the ETABS will design. Okay. So whatever the input I gave, see this in the ETABS also, I gave all the input: earthquake, go to define, and load patterns. I gave a earthquake and a wind load. So if you give the input, ETABS will give the output. So what ETABS will do for these calculations? How the ETABS will calculate the force, wind force. So if you don't know the manual calculation, how can you understand ETABS? How the ETABS will calculate the wind calculation? So try to learn the manual calculation. Manual calculation. Once you learn the manual calculation, then only you can understand the concept. So how the ETABS will do? Yeah, serious. So see guys, this is one of the wind load manual calculation. See, I mentioned as a formulas actually. So see this. These are the formulas, pressures for the procedure for the wind calculation on a static method. So see VZ, I already told you VZ is a VB is equal to K1, K2, K3, K4. PZ is a 0.6 into VZ square. This is the second formula we need to apply. So based upon this, so let's show you. Yeah, this is a VB. VB is a basic wind speed. If it is a suppose if my building is in a 50 kilo, so as per the 50 per meter per second, as per the Visakhapatnam in that table. So K1, K2, K3, K4 I decided. So after that second formula will be PZ. PZ is a 0.6 into VZ square. Okay. So PD. So if you come to the PD is equal to KD, KA, KC, PZ. PZ is mainly come from here. So once you come to the PZ, so if is a F is a CFAE into PD again comes from here. Okay, PC. So then you will calculate the kilonewtons. So initially it's a meter per second and the Newton per meter square, kilonewton per meter square. So it's kilonewton. Like that you can calculate the manual calculation. Okay. So and again come to the earthquake. So earthquake is the main concept will be base shear. Okay. I think we didn't go up to earthquake, right? So we will cover that one later. Okay. So I hope you understand it. And this is a part 4, right? Part 3. Yeah. This is okay. I hope you understand how the earthquake wind load will done. And let me. So these are the main 4 formulas will help you to do the manual calculation. Okay. So and come to the next one. Part 3, and these are the, and this is the amendment, actually amendment 1. So whatever the changes they made, they just write here. And after that, just go for the snow load. Okay. So part 4 is mainly for the snow load. Snow load in the sense, every time if you wanted to calculate the snow load, we need to calculate the depth. Okay. So and depth under some type of arrangement, roof shaping. And here you can see this. So every time if you wanted to snow load on roof, so you see this snow load S is equal to nu is equal to S naught. Okay, S naught, what is S naught? So come here. S is the design snow load in a PA, plan area of the roof, and U is the shape coefficient. How our building shape will be. And here is a ground snow load PA. How much is the load, snow load? How much is the unit weight of the snow load? So once you know that, either this you will know that. So every time our main concern is the shape coefficient. So how we can calculate the shape coefficient? So some shape coefficient for different type of roofs. See, shape coefficient for selected type of roof. If it is a roof, it is like this, and you will get a lot of formulas to decide the shape coefficient. Here is a 0.8 is a shape coefficient. Once you design with the unit weight into the load with the shape weight, you will get a snow load. Then you can apply in buildings with having a curved roof and like that. And here is a shape sample curved roof. If it is a curved roof, what is the shape coefficient? And again come to here. This is a multi-level roof. And again come to here, and the complex multi-leveled roof. Okay, and again here is some local projection of the obstructions, and this is a shape. This is somewhat different shape, and like that. Okay, it's not that much. Only 13 pages of a book. Only main important thing is shape factor. Okay, shape coefficient is the main important thing. How we can calculate the shape coefficient? Once you know that, so you can calculate the load with the shape coefficient. Then you will get a snow load. Okay, and come to here IS 17 part 5, dead load and load combinations. Okay, so load, special loads and load combinations. And once you go from here, and this is amendments. Amendment 1 is December 2006, and some first para listed sense and substitute the following for execution. And the crack supply propagate if the loading is a cyclic and repeated. These all things they added. And if you go to here, and here you can see the dead load, part 1, part 2 imposed load, and part 3 wind load, and part 4 snow load, part 5 special loads and load combinations. Okay, so and after that, this part 5 that deals with the loads and the load effects on other those covered in a part 1, part 2. Other than the part 1, part 2, whatever the loads will be there in our construction, so those will be covered in a part 4. And come to here, National Building Code and Canadian Code. This, yeah, I hope everything is clear. Okay, guys, sorry for the disturbance. Yeah, some the flying fragments and like that. And here is a collision between vehicles and structural elements. If any vehicle will hit the structural element, also due to that load also will consider. And here is a fatigue vehicle shall be, and all the information will be here. And the some explosions also. If any internal dust explosion and boiler failure and external gas cloud explosions and external exposure height extensive, what we need to do, and what type of effects will be acted on our building, those things we can see. Vertical loads on air raid shelters. Okay, so vertical loads and building up to 20 meters, 2-story, how it will be. And these all the information. And here you can see the fire fire also general and thermal effect during the fire, and fire resistance also we need to calculate, and load combinations. So load combinations in the sense dead load and live load, imposed load, and here is a impact load and wind load, and these all things, and how we can take in a ETABS. Okay, so ETABS also we have a wonderful option, load combinations. Once you go here, so once you click on add a default load combinations, once you choose a concrete frame design, click on OK. All the load combinations, whatever the loads you given, based upon the loads, you will get all the load combinations. Here you can see 1.2 dead load, live load, HDL plus wind load. And here once you go here, 1.2 dead load, live load, HDL minus wind. Okay, so like that we can take. And here is the envelope load. If you go for the envelope load, whatever the maximum acting on that building, so that will show you the in envelope load. Okay, so like that we can give the wind loads also. And we will go to the next concept. So this is a earthquake resistance. Okay, this is one of the interest concept actually. So every time, yeah, let me show you that. So here you can see the design horizontal acceleration and Diff. So whenever we are in some final year or working professionals, try to read this entire code book, earthquake code book. Then it will be gives you a wonderful concept, and it will be the interesting actually. So it's not like 144 pages. It's just a 44 pages. Okay, liquefaction. Okay, when it is primarily in a saturated conditions soil, then if any time earthquake will shake our building, whatever the water in the soil, that will create this liquefaction action. Okay, so under model mass and what is the modes in of the structure, model participation ratio factors, and these, and here is a model oscillation, mode shape coefficient, and again the seismic weight of the floor and seismic weight of the structure, time history analysis, and some mode oscillations, and peak ground acceleration, and response spectrum, what is the response spectrum R, and these all things. Okay, so on the response spectrum, I think something has happened. I took something. Okay, I hope it's fine. Again, go to here is the sum of the loads. See guys, these are the sum of the loads, assumption the load for the earthquake. And here anytime if you have some vertical loads also, you need to consider these load combinations. Okay, so some implies a set of combinations involving the earthquake effect considered shall be given below. These are the load combinations we need to follow. Okay, effect of due to the vertical earthquake shaking shall be considered any of the following the apply. See, this structure is located in a seismic zone 4 and 5. So structure listed on soft soil. So at the time you need to consider it, and again go to here. So design acceleration spectrum. But the main thing I need to tell you. So every time if you go for the base earthquake load, VB is equal to AH into W. That formula also here we have that formula. I didn't invented that formula. That's the formula actually here. Okay, so where I see, let me show you where the formula is happened. Okay, so I think here somewhere we have that formula, base shear. So where is the formula? I think I didn't see that. Yeah, somewhere. Okay, anyway, formula is same, no need to worry. So AH into W. AH in the sense design acceleration spectrum. So here we can see the again this formula you will get from here only. Okay, so and weight will be seismic weight, and let me show you that my manual calculation. VB is equal to AH into W. AH is a horizontal design coefficient, acceleration coefficient. W is the seismic weight. How we can calculate the seismic weight? How we can calculate the AH? And if you go for the AH, so we need to calculate a lot of the parameters. So Z, what is the Z? What 2 and SA by G, and RI. R is a, what is that? Response spectrum, response reduction factor, and I is importance factor. J is a zone factor. So let's discuss about zone factor. How we can decide which zone it is? So this is a table. This is a map for the zone design. So just zone 2 and zone 3, zone 4, zone 5. Okay. So in the zone 5, we are where we are in. So Nellore and Chennai, Puducherry, and I think Machilipatnam. So Vijayawada is in a yellow region. Yellow in the sense zone 3, right? Zone 3. Vijayawada is in a zone 3. Okay. So Vijayawada is zone 3, and also come to Vizag. So Vizag in a zone 2. Somewhere here we have a Vizag. Okay, somewhere in this area, somewhere I think. Okay, so this is in this zone. So that's why it's color is zone 3. So like that we can get the which zone it is, and here we have a table also. In that table you will get all the zones. So let me show you that table. Entire table will yeah, this one. So as per this, so is here Agra is in zone 3, and like Allahabad and Gorakhpur is in zone 4. 0.24 is the coefficient factor, and Hyderabad is in zone 2. And again come to here, and Srinagar is in zone 5, and Mumbai is in zone 3, Nellore is in zone 3, and Vijayawada zone 3, and Visakhapatnam zone 2. So let me tell you one thing: if it is a zone 2, so every time it's a zone 2, zone 3, zone 4, and zone 5. There is no zone 1. Okay, so there is no zone 1, only it will start from the 2 only. So if it is a zone 2, you are in a safe. Okay, no need to worry about it, worry about the earthquake. If it is a zone 3, you are also safe. Okay, and the zone 4, it's dangerous. Okay, so if it's zone 5, highly dangerous, we don't know when the earthquake will hit. So that's why as per this we will decide you are in a safe zone or not. Okay, and again come to our concept. We call it as ordinary film. This we will discuss after a few seconds.